Lastly, just like we did with time, we're going to think about extrapolation to larger spatial scales. So before, when we did measurements on relatively short time scales, we thought about what it took to take a short-term measurement and extrapolate out to longer time scales. And the same thing is going to happen here. We're going to think about doing measurements on a relatively small spatial scale and what it takes to extrapolate them out to larger spatial scales. So essentially the question that we have is, how do we take plot level measurements and extrapolate? Is there a trick to this? Is it pretty simple? Or are there new things that happen once we actually try and take our plot level measurements and extrapolate them out to larger scales? Extrapolation of ecosystem processes to large spatial scales requires an understanding of the role of spatial heterogeneity in ecosystem processes. So one way to do this is to simply assume that the places that we measured are typical and multiply it. And just like the idea that you can do a measurement over a minute and multiply it by 60 minutes, 24 hours, and 365 days to get to the annual scale, that's one way to scale up temporally. And on a spatial scale, if we assume that it's typical, we just might take a measurement on a single meter squared, something like that, and extrapolate that up to the kilometer squared just by multiplying by 10,000. And often what we do is essentially a back of the envelope calculation. We take the numbers that we have and we simply scale them up by multiplying over the different areas that we're trying to extrapolate to. Another approach is simply something referred to as a paint by numbers approach, is that we can divide up an ecosystem into different patches and do measurements within each of these patches. So patch type 1 we can do measurements in, and the matrix 2, and get different measurements for 1 and 2, and then multiply the values that we get for each of these by the relative amount of areas. And that's not a bad way to do things if we know what the differences are among the different patches and can measure differences in the rates. When we do this, it's important to think that we're trying not to miss hotspots. So to get a good average for a large area, we have to find where the hotspots are. And these are going to might have a disproportionate effect on the average because they have such a high rate. When we start to extrapolate over large areas or under novel conditions, we really need to use process-based models. And part of that reason is that we can do measurements on small scales, and we can do a paint by numbers approach, for example. But there are new processes that occur as we get to larger and larger spatial scales. So we might ask what happens in that same area if we expand the amount of type 1 versus type 2, and you get a larger proportion of type 1. If there's new sets of processes that occur at these larger spatial scales that weren't occurring here, our process-based model needs to take that into account. We might not be able to measure it, but we can ask if this area is going to expand in size, what new factors are going to happen. And it's the same sense that we had for temporal scaling, that once we went to longer and longer periods, there were new sources of variation that were present on those longer time scales. And the same thing happens when we go to larger areas or even these novel conditions. We really take the information that we have and put them in to process-based models. The authors also say that remote sensing has been really helpful in our extrapolation. It's really hard on the ground, once we do a measurement, to know what proportion of the landscape is under one type or another. But with remote sensing products, it makes it a lot easier to extrapolate out. That being said, some things cannot be remotely sensed. And so in that case, remote sensing is important, it's an important tool, but not everything gets fed into models and extrapolated out simply via remote sensing.